Okay, let me start by thanking the organizers for inviting me to this wonderful conference and to speak about some recent work that I've been doing with many collaborators. Some of them are in the audience. So yes, I'll talk about how to compute gravitational waveform from the scattering of two massive objects flying by each other and slightly deflecting, so far away from each other. The first result in this direction was actually from Kovacs and Thorne in the 78, and in recent years it has been resurrected first by the Berlin group and then people in Paris, and later by other groups, including spin corrections. And then in the past 2 years, we have seen a lot of developments on the computation, the understanding of the gravitational waveform to next to leading order in this post-Minkowskian expansion. So here you can see some nice graph, which actually is not from me, it's from Aidan, Radu, and Fei. And here you can see the metric on the celestial sphere and some blimp remaining there. This is the so-called memory effect. Okay, so why gravitational waveforms? So we know that actually to measure gravitational waveforms, we need gravitational waveform templates to isolate the signals from the background noise. And then the natural question is, why scattering? As we said, there is, you can connect the results from the scattering because the scattering allows you to get results for generic velocities. You can connect this result with the result for the bound states. But also, scattering setups are interesting on their own. There might be a chance to measure them in the future. On the other hand, these objects are also very interesting. They have very interesting analytic properties, which are connected with the analytic properties of the scattering amplitudes. So we would like to study them more. Okay, so how do we compute these gravitational waveforms? The recipe is given by an on-shell version of the in formalism, which is referred to K-Mock formalism, where we compute some expectation, the difference of the expectation values of some operators in the far future and in the far past, where we relate some initial state in the far past to in the far future to an initial state in the far past by the S matrix. Now, since we are interested in the two-body problem, we have to choose carefully this initial state. It will be a superposition of two particle states where the wave function pick for us the classical limit, which correspond to taking the Compton wavelengths of this object much smaller than the Schwarzschild-Reddy. And then since we want to access these observables in perturbation theory, we consider the object far away from each other. Now, which is the operators which give us the waveform or a proxy for the waveform, let's say, is actually the linearized graviton field contracted with the polarization tensor. One can actually see that this operator is gauge invariant operator if one restricts on diffeomorphism which vanish at infinity. So the final formula is something like this. The waveform is basically a Fourier transform of the 5-point amplitude plus an extra term, which is sometimes referred as the K-Mock cut. Actually, one can notice that the Feynman rules for this guy are exactly the same Feynman rules for this, but the I epsilon prescription are slightly different. So what this term is doing for us is actually changing the I epsilon prescription of this in-out observable to make it an in-in observable. And this was studied in this very recent paper. Now, there is some unpleasant feature that is the I mean, once you have the amplitude, the in-version of this amplitude, you have to compute a very non-trivial Fourier transform, and this can be painful, and I'll talk about this at the end of this talk. So, yes, let me show now a more than 1-year-old result obtained by various groups, first in the scalar case and later also with spin correction, linear spin corrections. We obtained these results using some heavy mass effective theory, gluing these 3-level amplitudes using generalized unitarity, and then since it is one loop, you can basically integrate these Feynman integrals as you prefer. The result look like this. It's pretty simple, you would say. There are a bunch of logs, a bunch of square roots. Now, here I'm putting part of the result. So the part which is proportional to, it has some particular power counting in the mass. In this limit, basically the mass is counting the powers of h bar. And here I'm not including terms which explode when h bar goes to 0. But okay, because these terms cancel between these two terms, the amplitude and the cut part. Now, the first thing you should notice is that both the amplitude and the cut part are infrared divergent. The infrared divergences don't cancel each other exactly. Actually, they have two different origins. This is the infrared divergence of Weinberg. The second one, is basically the Shapiro time delay of the observed radiation. And the second one is actually a new infrared divergence, which is specific of the in-observable and is basically originating from the logarithmic drift of the world lengths in the far past. As I said, these results seem quite easy to handle, but if you look at these rational coefficients multiplying the logs, actually you see that each of these rational coefficients has 100 or 1,000 of terms, each of which have their own spurious poles, and they are spurious poles because on the principal sheet of the amplitude, there is some non-trivial cancellation between the coefficients of the different logs, so the different logs combine, and there is some magic cancellation, so these points are completely smooth, but this is not manifest at all. There is also a second unpleasant feature is that many of these terms actually are, after we Fourier transform them, are completely useless because they will integrate to delta function of B, where B is the impact parameter. So they are contact terms which are not computed reliably within this classical approximation. So yes. So okay, this was our result. And actually, some people from the GR community asked, but is this result compatible with the results that we get from GR, from these multipolar post-Minkowskian computations? And they immediately faced the technical problem coming from these spurious poles. So when you expand this amplitude in the small velocity limit, you see this P infinity is the small velocity expansion parameter. You see that each of these terms diverge very badly, but actually this divergence comes from these fake poles. So there are huge cancellations. Each of these terms are monomials in the kinematic variables, and to get a single the first non-trivial order in the small velocity expansion, you actually have to expand all of these terms to the 12 plus 1 orders in the small velocity expansion to get just one. This becomes very quickly intractable. I mean, you can try to use some partial fractioning or some finite field reconstruction with a better ansatz where these spurious poles are disentangled, but I mean, this makes your life a bit easier, but not that much. This is not just an analytic problem, it's just a numerical, it's also a numerical problem because these poles sit exactly on the physical region. So when you try to do the Fourier transform numerically, different terms explode, and there is a huge cancellation between the intermediate terms, and actually the numerics is very unstable. People in the audience have developed some way around, but still. I mean, one idea that we used when we compare to numerical relativity, to general relativity results, is to use an idea from Zvi, Lance, and David from long ago. So write the amplitude in terms of new set of functions, which actually is a combination of combinations of logarithms where the spurious pole manifestly vanish, and this was allowed us to go very high to very high order in the small velocity expansion. So let me just give you a quick review on how these computations are done in the general relativity approach. So basically, this multipolar post-Minkowskian formalism computes the time domain waveform as a sum of some irreducible multipolar contributions, and by some kind of matching, very similar to an EFT matching, you can express this multiple contribution in terms of the stress energy tensor of the material source. So we have some local in time term, some nonlinear term which comes from the fact that general relativity is nonlinear, plus these are the general relativity version of what Zvi was calling the tail terms. So these contributions which actually depend on the full history of the system. And then the stress tensor is basically given by evaluating by the equation of motion of the source expanded in the small velocity. So the first thing you have to do to try to match these two results is actually, since they are computed in a slightly different frame, you have to perform a rotation. There is this difference of frame between the two results. Actually, there was a very nice paper by also some people in the audience where they showed that this rotation is actually equivalent to the K-Mach cut term. So in principle, you can compute just the amplitude, and at this order, at least at one loop, you can compute just the amplitude and not perform the rotation that would match the NPM result. But some extra subtlety comes from the fact that these these results are infrared divergent. They have scheme dependencies, and actually you have to take into account some epsilon over epsilon contribution, which come from the epsilon degrees of freedom of the internal gravitons. This was not all. This was enough to very high order, but there was still some disagreement. The first thing you have to notice is that in the NPM you have the leading term is a constant in time leading term. So in the amplitude approach is basically including a one particle graviton emission at zero energy. But then you ask yourself whether this term can back react. And actually, we split the contribution of the momentum space waveform in terms of three terms: this constant term, the connected term, which is the one that was showing before, and a disconnected term, where you have basically in the cut term the zero energy graviton mixing with the 6-point amplitude. Actually, there is a nice connection between these zero energy gravitons and the BMS frame. So if these zero energy gravitons are kept in the spectrum, now you have to include them into the cuts. And this integration is not very well defined. So you have to put this leg slightly off shell to include the zero energy graviton in the phase space integration. Once you do that, actually you see that you have an extra term which depends on the off-shellness of this leg, but this extra term can be reabsorbed in a definition of what you mean by t equals 0 in your experiment. So it's a redefinition of your retarded time plus a new term, and this new term actually looks like exactly a BMS supertranslation, the one that was described in this paper by Venezian and Vilkovisky, and later in connection with the waveform by Gergudis, Eisenberg, and Russo. After you take into account all of this, you understand that there are a bunch of subtleties. The results start matching exactly. But still, okay, the result is good, but we have it in a kind of useless form in the sense that unless we take the small velocity limit, we don't know how to compute this Fourier transform. Because, I mean, it's very hard. This spurious pole makes your life very hard. So one thing that I've been looking at more recently with Giacomo in the audience was some improved framework to compute this Fourier transform. The first thing you want to do is actually get rid of all the analytic terms in Q1 and Q2 because they will integrate to delta functions. And if you actually use the analytic properties of the scattering amplitude or this observable, you actually notice that you can isolate the non-analytic term by looking at cuts in the Q1 and Q2 complex plane, so outside of the physical region. And basically this was used, we introduced this in a paper where we computed the 3-level waveform with spin. But actually there is a nice connection with a talk by Andrew that, would it be possible to compute just the discontinuity of the Feynman integrals without going through the computation of the integrals and then analytically continue and compute the discontinuities? The trick also was, once we know that the only thing we have to do is changing the I epsilon, we compute the amplitude, and then we change the I epsilon by n. This was an easy fix. Now, we want to avoid the spurious pole to appear at the level of the Fourier transform. So we take the Q integrals, which are these momentum transfer or momentum mismatches. We treat them as loop momenta, and we perform some tensor to scalar decomposition at the level of the Fourier plus loop integral. But then we notice that we can also use IBP relations, like the same in dimensional regularization, the same IBP relations developed for loops, but now with an extra exponential factor. Very nice fact is that the IBP relations with an exponential factor are just linear combination of normal IBP relations as the exponential factor was not there. So we didn't have to build any new program to deal with these IBP relations. We just needed some packages developed for multi-loop computations. At this point, basically, we reduced the waveform in terms of a bunch of master integrals, which are basically Fourier transform of the loop master integrals and their derivative with respect to the impact parameter space. So basically, all the spurious poles now appear outside the Fourier integration, and they give no problem. So we had to compute these Fourier integrals. I mean, here I'm showing the integrals that appear in QED. Most of them are pretty easy to handle. They just give Bessel function, but there is some new funny family of functions that appear. For example, the Fourier transform of this integral is these very interesting integrals over a Struve H function, which is basically a Bessel function. Now, there are two natural questions, like can we write this Fourier transform as some new iterated integrals like we do for loops, or can we actually, instead of treating at the end of the game, we after reducing we treated the loops and the Fourier integrals separately. So can we actually treat them together and write differential equations and find a canonical form for it? Okay, just let me summarize. So I showed you the computation of the next to leading order waveform in momentum space. There was this very nice synergy between the amplitude community with the GR community, where we learned a lot, and we found this very interesting connection with the BMS. So this was very fruitful and instructive. And also, I showed you some new way of getting the analytic wave in impact parameter space, which will be essential, for example, if we want to go to next to leading order, where the spurious pole will be even worse. Then we have to ask, is some interesting feature that we are going to learn from this computation, but since this is a very hard computation, like is a two-loop 5-point computation, like which is basically the cutting-edge research in QCD. But if you include also the Fourier integral, is basically a bad three-loop 5-point computation. Some interesting question is also whether we can capture from amplitudes terms which are beyond the 1/r expansion of the waveform, whether we can find some method to resum our result similar to the EOB and compare it with numerical relativity. And I would like to close this. I mean, since yesterday we spoke a lot about continuous spin at the discussion, even more than black holes, probably you should stay tuned and look for our coming paper on continuous spin in the next weeks.
Questions?
Thanks for the great talk. Just a question, when you include the zero frequency gravitons in order to get the right coefficient, say, in front of the BMS transformation, do we need to include them just in the KMOC cut or also in the cuts that the amplitude already has, right? In the imaginary parts of the amplitude itself? Yeah, since this is exact, so it doesn't need any loop correction, so you don't need to include it in the... No, I mean in the diagram that you drew, I think. Yeah, that no, one. That's all you have to do. All the other cuts are either vanishing or taking into account, like correcting this, but this is exact. Thanks.
No more questions? Okay. Thanks again to Stefano.